All right, I'll make a start. I'm Thomas, and I look after the Vibrational Spectroscopy facility in the CSL. We actually have a few different spectrometers in the facility. We have got infrared spectrometers, near-infrared spectrometers, or NIR, and also Raman spectrometers. So I'll quickly go through each of the techniques with a little bit of theory and a few examples, just to give you sort of a little bit of an understanding of what we can and can't do. Infrared spectroscopy, it's fairly simple in its basic setup, in that you have a light source, which is a little bit like a light bulb, but it emits infrared light, so not visible to the human eye. The light travels through the sample chamber here. In this case, I've got a little plastic film, polystyrene, in the middle. The sample will absorb some of the light, and you detect which light comes through the sample with a detector on the other side. So, in principle, fairly simple setup. The inside of the instrument does look a little bit more complicated, but in a nutshell, that's all there is to it. Infrared is a technique that's actually really sensitive, in that you don't need actually a lot of material for the whole infrared light to be absorbed. And so if you do this sort of transmission measurement, we actually need a really thin film. That's often not the case with real samples. So we do have a few other gadgets at our disposal to measure samples. This one here is called an ATR attachment, where we simply can place any solid or liquid on a crystal and measure the infrared spectrum straight away without any further sample preparation. We also have a diffuse reflectance autosampler. This is very useful, for example, for soil analysis, and we're just sort of conducting a fairly big national approach with carbon in soil, where we're able to measure all sorts of different carbon simply by using mid-infrared spectroscopy, and then using existing models that were developed on a national basis to predict what certain carbon values you have got in your soil. So very handy attachment. We also have a microscope attached to the instrument, so we can look at really small particle sizes within a sample. If you do sort of a spot analysis, we can go down to 5 by 5 microns. We're just about to install also a focal plane array detector for the microscope, which gives us sort of an instant image shot of 4096 pixels, and the spot size for each pixel will be about 2.5 microns. You can't really go lower with the spatial resolution, purely because there's a diffraction limitation with the light. So it's simple physics that you can't actually go lower in spot size. So this is really the limit you can sort of go to with infrared spectroscopy. And what it enables you, and I'll show you an example in a minute, is it's specifically useful for actually imaging. So to look at the spatial distribution of certain chemicals within a sample. That's where especially the FPA detector will come in very handy. This is a typical example of an infrared spectrum. So this is of that polystyrene film that I showed you earlier. Lots of very well-defined peaks, where there's essentially almost 100% transmission. That means at that particular wave number or wavelength, there's not much happening. At certain wavelengths or wave numbers, we see some sort of absorption. And these spectra can be quite hard to interpret, in the sense that either you need to be very experienced spectroscopist who then looks at it, yep, that looks like polystyrene, or you use this sort of fingerprint region and do library searches for identification. So this is really, especially that region is almost like a fingerprint. So any sort of chemical that you've got is very unique in its fingerprint region, and you can identify it if you've got a comprehensive library. So often this sort of tool is used as a first point of analysis for very unknown samples, a la CSI on TV, when you've got crime scenes and they want to identify certain chemicals at the crime scene. There's a lot of real good science in CSI, and infrared is usually one of the toys that's used straight up. To show you some real examples that we can use, this is simply a two-polymer system, and this particular company had problems by mixing these two PHP and PLA polymers to actually get a homogeneous polymer. And if you look at the individual spectra, we can actually differentiate both of these polymers simply by certain characteristic peaks. So this bottom part is the overall spectrum that you get, but the component of this peak is made out of component A and component B. And when you then image it with our microscope, let's say in the case of a 50-50 mixture, you can actually see it's not a homogeneous mixture. It actually used these sort of globules almost of the PHB, and around it the PLL sort of formed. And that was not desirable. It wasn't until you go to a 30-70 mixture that you got a fairly nice homogeneous mixture. So this is one of the applications, very simple to really visualize your spatial distribution of certain chemicals within a sample. And it doesn't have to be polymers, because infrared is sensitive to all sorts of, especially organic matter, but even inorganic matter. The only thing we can't really measure is pure metals. So pure metal, but that's probably not really of interest to agriculture science anyway. Here's another example to show you more of a high resolution image approach that we can do to differentiate, let's say, proteins and lipids. This is a cross section of a hair. So you can see this is 10 microns. So we can go down fairly low in resolution and actually pick up some of the finer details of a lipid protein distribution. And again, what you do is you concentrate on your characteristic peaks for both of these chemicals and image essentially where these chemicals are present. This is another example where we imaged bacteria growth. The idea is to actually form a homogeneous biofilm. So clearly at this stage in the project we were not very successful, but it just shows the fine details that we can actually pick up with our microscope and the distribution of the bacteria growth. Important to point out, this was actually done prior to our FPA, so that's actually only 784 pixels. With the FPA, once it's online, we can do the same image in the same time, but we will get about 2 million pixels. So that will be a vast improvement on the technique. Okay, let's go to near-infrared. I showed you the spectrum of polystyrene, which I've got on the right-hand side here in red again. So you get these nice defined big absorption peaks. The near-infrared, on the other hand, so that's 2 scale of the same material, is this not very exciting looking spectrum down here. So not very well defined, broad peaks, not very intense. And what it actually is, they're not direct measurements, they're actually combinatorial and overtone peaks out of that mid-infrared region. Okay, so if you've got a certain frequency, let's say about 2,900, you double it, you get a peak at about 5,800, okay, which is sort of an overtone, and you get combinatorial peaks. So why is near-infrared so useful? Well, if you remember what I said about 5 minutes ago, we actually do struggle with normal mid-infrared with sensitivity. You don't need much material to get complete absorption of infrared light. So near-infrared being not as sensitive is actually a really good thing, because it means we don't actually have to worry about much about sample preparation. And this is our near-infrared spectrometer. So for example, what you can do is this is crushed up grass, cattle feed in a glass vial, and we can simply measure the near-infrared spectrum inside the vial. So through the glass, the light comes through the bottom, it scatters back to the detector, and that's how we measure it. So you never have to even get the sample out of your vial. And that's simply something you could not do in infrared. We also have an optic fiber probe here, optical fiber op probe, where we can simply point to anything that we want to measure. So you can bring samples up to the instrument and we can measure it through the fiber optical probe. We also have other gadgets. We've got a big auto sampler, for example, for wood cores that we used while forestry CRC was still active here. So they're great toys. We have got a big auto sampler that we use for grape wines, for example, where you can simply put grape wines or any sort of grain in there. You don't need to crush it up. It will actually homogenize it by rotating that big vial around, and you can just simply analyze grains or anything like that straight up. You don't need to do any further sample preparation with it. This is sort of a typical example of a near-infrared spectrum of a leaf from an acacia plant, and firsthand it doesn't look, as I said, very exciting, because you get these sort of broad, non-descriptive peaks, and even as an experienced spectroscopist, I look at it and go, at best I might be able to give you an answer that looks like a leaf. And it looks like a fresh leaf, it doesn't look like a dried leaf. but that's probably as far as I can go. And as it turns out, with this particular project, we were actually interested in classifying. We knew that about half of these samples should have been a diploid plant and half of them should have been tetraploid. And so the aim is, can we differentiate the two by looking at the spectra? Now you look at the spectra and you probably go, no, there's just no way we can do that because they just look all the same. And this is sort of where a little bit of spectral manipulation comes in. I've got a particular band here out of the mid-infrared region, which we call the AMAT1 band. And if you have a close look at that overall curvature, you can actually see it comes sort of with shoulders and bumps. And that's because there's actually a lot of information under that broad peak. Okay? We have got all sorts of different information that comes out of that AMAT1 band that has to do with all sorts of different characteristic peaks. So how do we identify these individual peaks? Well, if you look at that sort of broad setup of a spectrum, it's the first derivative and especially the second derivative of a spectrum that really unlocks some of that sort of broad features in the shoulders to actually identify individual peaks. So with near-infrared spectroscopy, you do a lot of spectral manipulations in order to actually unlock some of that sort of hidden information that's inside your spectrum. So if you go back to our leaf samples, so we just look at this one single peak here and do a second derivative of it, and it will look actually exactly like this. Now you might say, that looks like noise, but there's actually some real spectral features in here. And when you do a PCA analysis, for example, of that, of these spectra with a second derivative, you could actually absolutely easily on factor 1 differentiate diploids from tetraploids. So a very powerful analysis tool in that sense. It's also a great tool for quantitative modeling. So here we have our cattle feed again. So you want to know ADF, NDF, protein, even trace minerals. What you do is you create quantitative models. So you scan about 100, 150 NIR spectra, and you do need to go the hard way and analyze your ADF, NDF, proteins, and so forth with the classical means. Once you have that, you can then correlate the numbers against your NIR spectrum and come up with these PLS regression models. And usually you get very good models. So good data into the model means you get usually good models out. So a very powerful tool. And what it means now is simply you get this sort of glass vial. You've got an auto-sampler, and within seconds you get all the answers in one hit. Very cheap, very effective, very fast analysis. But you do have to go and create these initial models first. And where it gets a little bit complicated is when you, for example, get regional effects, seasonal effects. So you might have a brilliant model that worked for 2012. Now you want to predict 2013 samples. You might get an issue. But all it means is you might have to include another 50 samples into our existing model and build what we call a more global model. And over the years, you actually overcome these sort of seasonal effects, and you have a very robust global model. The software that we use mainly is Unscrambler, so it's a very powerful statistical program that allows you to do a lot of spectral manipulations that we talked about, and also all sorts of different statistical analysis that you might want to do, from clustering to regression modeling, PCA analysis, and so forth. These are some of the examples that we have used in the past where NIR has been used, and the first one where we, for example, you looked at microbial spoilage on salmon. Just to give you an example how easy it is to take your NIR spectrum. Literally, this is just a piece of salmon from the supermarket. You put it under the fiber optic probe, we measure it, that's it. So in theory, you could take it home now and have a nice piece of salmon because literally you didn't do anything to it. We've used it in the wine research. Bob Bambergs obviously is a guru in that area and uses mid-infrared and near-infrared quite a lot. Classification of eucalyptus species. We have done some work on barley. Also in chemistry, we have a look at the paper chemistry, and obviously with forestry CRC gone now, there's still a private entity that uses existing models for forestry products. So quite powerful technique. So let me quickly introduce the last instrument that we've got in the series, Raman spectroscopy. This is our latest sort of new toy that we got in 2011 through ARC funding, and it's a great instrument. What you actually get out of it is a very similar looking spectrum. So what I've got in red is actually the infrared spectrum that we've seen before of polystyrene. Down below is the Raman spectrum in blue. And you can see for the majority of it, you actually, where there's a peak in infrared, you also get a peak in Raman. But there are occasions, for example, especially the strongest absorption peak in infrared, you don't see anything at all in Raman. And vice versa, you get peaks in Raman where there's just nothing in the infrared. And this has to do with selection rules, group theory, and I won't bore you with it. Needless to say that both techniques are very complementary, and the resulting spectrum is somewhat related. But how you get the spectrum is quite different. But I won't go into details due to time limitations here. Just to give you a couple of examples, again, similar to NIR, the great thing about Raman is you don't need to do sample preparation either. So in this case, Raman was chosen to look at fatty acids and the distribution of certain fatty acids within cow's milk and create this sort of modeling again. And the great thing about Raman is you get them as little handheld instruments as well, or you can use fiber optic probes. So very easy to use sort of out in the field or even in industrial applications. And the modeling that we talked about before also applies for Raman, so a very powerful technique. Again, where our instrument comes really to fruition is probably your imaging. So the spatial distribution of certain chemicals. In this case, for example, we have caffeine, aspirin, and paracetamol in a pharmaceutical tablet. That only took 4 minutes, to do. It's probably a couple of centimeters long tablet. So it's quite easy to do. The Raman is also great with the spatial resolution in that we can actually go sub-micron. So other than the infrared spectrometer, we actually use visible lasers to achieve our light scattering. That means that we can actually go much lower than 1 micron resolution. So this is an example of some bacterial cells that we could image. And where it comes in really handy, Raman is a confocal technique. That means then when you use the microscope and you look at a sample, we don't measure necessarily what's on the surface. If that's what's in focus, that's what you will measure. But if you go below the surface, you actually will measure the spectrum that's below the surface. And I had an example recently from Plant Science. They had some crystal growth in some of the leaves of some succulent plant. And Noel sort of had a crack at it trying to identify it, but they had to isolate the crystal and it wasn't very easy. With the Raman, it was actually very easy to do because all you had to do is you take that piece of leaf, you focus onto the crystal inside the leaf, take the Raman spectrum, you got a very clean Raman spectrum, we could identify it that way. Which was, from memory, just I think a calcium hydroxylate or kind of oxalate. That's right. That's what it was. But in this case here, that's a geological one. That's a microdiamond. That's an inclusion inside the rock, and the white bits are actually imperfections within that microdiamond. But just to show you that you can actually get a full 3D image, chemical image of your sample using confocal Raman microscopy. Just very quickly, this instrument I also look after has nothing to do with vibrational spectroscopy. It's our organic elemental analyzer for carbon, nitrogen, hydrogen, sulfur analysis. Probably the thing really to point out, it's a very simple technique to get your high precision carbon, nitrogen, hydrogen, but it does require really a qualified operator, and that there are really big pitfalls with this sort of instrument. So unless you really know what you're doing, you just get out numbers at the end and you believe them. So it does actually take quite a bit of knowledge to operate this instrument. So just another service that we've got available here in the CSL. And that's the end of my talk.